Again, and welcome to a video where I describe how to accomplish Project 10. This is probably the most challenging project in our C class because this is a project where you actually make use of pointers to create a singly linked list, which is a dynamic data structure that you can create using pointers that can grow and shrink. Ours will only grow as needed while the program is running. Now, you've seen pointers before, char star pointers to characters, and you were maybe passing those around to the various C functions like strcomp or stir. But this time, we're actually going to use the pointers more dynamically to allocate memory, read a struct from our .dat file into that allocated memory, hook that new struct into a list of structs, and then when we're all done, when we read all the structs from the file, we're going to go through and print out the list of structs. So that's what's known as a singly linked list. It's called singly linked because you only have one pointer, as you'll see, between nodes. They're all strung together, as it were, with one pointer each. There are various other kinds of lists, like doubly linked lists, that we won't go into, that have pointers forward and backward. Our list can only be traversed, that is, can only be read in one direction, but that's fine for what we're doing. Let's start with a quick review, dogs.h. I'm using the dog structure. I've talked about it in another video. Nothing special about this. It's got all the attributes I need, all the members I need, structure members, to characterize a single dog, and it's type def, so I can use that name dog as if it were a built-in type. Here, it's being hash included, so we're pulling in that definition, so we're not retyping it. We're using the one from the struct. Here comes the twist, and this is takes a bit of getting used to. I'm actually going to embed the dog struct inside another struct. Well, why would you do that? You do that because in addition to all the attributes of a dog, the name and the fur length and the age, you also, to create a linked list, you also need a pointer, a next pointer, the pointer that lets you connect the list elements together. Now, there's another video in this section that shows you graphically how this list is constructed. Basically, I draw a picture, I sketch a picture of how this is going. You might want to take a look at that first, but this is the definition here, this type def. This creates a struct called a dog node. So we have a dog. That's just the information about the dog. We have the dog node, which is all the information about the dog, plus a pointer that lets me connect that dog to the next dog. So this is important because keeping in your mind straight between dog and dog node is important. And if you get it confused, it's going to mess up your program. Dog is what you read, fread from the file. All the file has in it are dogs. However, once we read in a dog, we need to put it into a dog node so that we can then put it into the list. So and these are different sizes, right? The dog node is 4 bytes or 8 bytes larger than a dog because it has the pointer in there. You can't read directly, you can't fread directly into a dog node because the .dat file you created in an earlier step doesn't have any pointers in it. It only has the dog information itself. Okay, so here's another type def that just makes it easy. I made a thing called a dog node pointer, which is a pointer to a dog node. This is now you don't have to do this. You can type out struct star everywhere you want. However, it seems a lot easier to read the code if you use the type defs. So once we get into main, I declare 3 pointers. And you'll recall from the earlier video, you need 3 pointers to create a linked list, plus the pointers that are in the struct. Temp, which is the pointer we're going to use when we're working. It's the pointer that's going to point to the new structs that we memory allocate as we're going along. We need head, which points to the very first dog in the list. And we need tail, which points to the last dog in the list and moves as we continue to add dogs. Those 3 pointers are all going to change. Well, head won't change, but tail and temp are going to change as we go forward. I open the file, dogs.dat, for read. You saw this in Project 9, exactly the same code. If it fails, I quit, and again, just like I did in Project 9, I should say print a message for myself. Couldn't read dog's file, because it's easily possible to have trouble opening a file because there are so many typos you can make. And believe me, I've made all those typos. I'll save that. And okay, let's get started. This is where the building the list actually starts. Okay, the first node is a special case because in the very first node in the linked list, all the pointers are the same because there's only one node. So it's the head, it's the tail, and it's the temp. So I use temp to get a new dog node. Now notice this is size of dog node, not size of dog, because we don't, in addition to needing the information about the dog, we also need the pointer, and only the dog node is big enough to hold that. Then head gets temp and tail gets temp, and result, which we're going to see in a minute in the while loop, gets 0. So now we're set up. There's no data in our dog yet. It's like an empty dog, if that makes sense, but the list is ready to be created. The while loop on line 38, it reads each dog from the file. And it looks a little confusing the way it's written, but let's step through it. Here's the fread, which is exactly like the fread we did in the previous, in Project 9. Fread fread a dog, one dog at a time from the file, and notice we're putting it in temp. And what was temp? Temp is a chunk of memory that we got right up here with malloc. So we dynamically allocated a place to put the dog. The result tells you how many dogs you read. And since we're only trying to read one dog, the result is going to either be 0 or 1. If it's 0, we've read all the dogs in the file. If it's 1, then it worked correctly. So while this whole thing is greater than 0 says basically while there are still dogs to be read in the file. That's the logic to actually read the file struct by struct. Notice it's size of dog here, not size of dog node. If you use size of dog node here, you'll get out of sync on the second dog, and things will get really strange. Here's where we hook temp into tail. So tail's the last node on the list, and tail is going to be connected to a new node. The new tail is now here, and here we're going to malloc again a new dog node. So the next time around, so this fills in the first dog. The second dog is going to be read here. It's going to be connected into the list, and so forth and so on. So I urge you to take a look at the sketches in the other video, the visualizing video, to see what's actually going on here. Finally, we're going to get to where we don't read any more dogs. The result is 0 because we read, say, 5 dogs. At that point, we're going to make the tail, the next pointer of tail, null, because that's the absolute end of the list. There are no more dogs in the list. And we're done. We built the list. Now, to know whether you built the list correctly, about the only way you can tell, unless you want to do a lot of debugging, is to go through and print out the list or traverse the list. That's pretty easy to do because of the way the list works. Where should we start? We should start with head, because head always points to the beginning of the list. So using temp, we set temp equal to head. And then while temp is not null, well, if there's any items on the list, it won't be null. Print out some information from the dog, that particular dog, and then use the next pointer to get the next dog. Eventually, we're going to come to the tail of the list. And remember, the next pointer of the very last dog is null. That's going to stop the loop up here. And that's going to basically be the end of the list. So let's save and compile this thing, because I did make one change, and run it and make sure that it works. So I'll save it. And I'm going to compile it in the terminal as I have in the past. which means you get to see all the nice command line stuff. So let's compile as a command line using GCC. Read dogs list .c. Okay, no error messages. That's always a good sign. That creates a new a.out file. There it is, brand new a.out file. Remember, that's the historical name that the command line C compiler gives your executable program under Mac OS and Linux. It'll be named something.exe in Windows, which will be actually makes more sense. I'm going to run that program, and it's hopefully going to read my dogs.dat file up here and build a list of dogs and then print out the list of dogs. And sure enough, there's the same list of dogs that we saw in the Project 9 approach, where we used an array, but this time we have dynamically allocated each dog. So that happens. You might ask, well, why would I want to do this complicated way when the simple way in Project 9 will work? This is handy if you have a very large number of structs to read in and you don't know how many there are. This way, in the Project 9 approach, you'd have to allocate an array. Say you read dog structs regularly. Most dogs.dat files have like 5 or 10 dogs in them, but every now and then they have 10,000 dogs in them. It's like the animal shelter or something. If so, you'd have to declare here max dogs to 10,000. That's a lot of memory that doesn't get used 99% of the time. Using this dynamic memory approach, you'll only allocate exactly the number of dogs that are in the current dogs.dat file. So that will certainly save a lot of memory. Also, it's important to free the memory that you've been using. I'm not doing it here because this is a one-time program. It runs and exits, so it won't leak. But if you have a continuously running program like a server, it's important to also free the memory that you mallocked when you no longer need it. And that kind of memory management, which you must do manually in C and C++, is tricky. And actually, the good news is Java does that for you automatically. So Java is an improvement over C and C++ in that one respect. However, in this case, we can get by with just F closing the file and being done with it. So if you use this code or this approach, remembering the critical points are to get this dog node struct right, and then to get your pointer structs right, I think you can accomplish this project without too much difficulty.